This is part 2 of a 2-part podcast.
Hey, this is T. Blankenship. Have you seen the new video of Wheaton Labs? It is permaculture awesomeness with all new and improved things like more rocket mass heaters, easy bake coffin, Willy Wonka, rocket cooktop 2.0, and the truly passive greenhouse. To see more, go to permies.com/tour. Again, that is permies.com/tour.
Back to rocket mass heaters.
So this is an area where you and I disagree, and this disagreement is delicious.
Mm-hmm.
Now,
and either one of these will work. This is working great, and what we're going to see is what will work better next.
True, and this is a system where we can do things. We can make changes. We can optimize this. Whereas the previous 4 builds, it was like, can't even optimize with this. We could optimize the previous builds, but we could only go so far. Whereas what we have right now, we have oodles of room for optimization.
Right.
So this is this ability to optimize as needed is a thing which I think is the beauty of the J-tube. It's like the whole J-tube design in general still has mountains of room for optimization, and it's so simple. And I truly believe that the standard J-tube builds, these are going to be the thing that transform the world, because they are so easy to build and so cheap to build and so quick to build. It's like this is what's going to take over the world. Batchbox is wonderful in the right conditions, but you gotta generally expect it's a much more sophisticated build. And anyway, that's another conversation for another day. All right. Digging into this. The cob hat. What I want to do is I want to make our existing system less efficient, which means there will be more heat going up the vertical exhaust. So it'll make for a much stronger draw in the system overall, which means less heat will be captured in the system. So the whole system will become less efficient at holding on to heat. But I kind of feel like this is something that's important to me when you're in a cabin. So to help mitigate the cold starts. So, but I kind of feel like if we put a wonderful cob hat on here, then we're going to have the benefit of the existing mass plus the benefit of the cob hat. But if I could just make the system a little less efficient in other places, then we'll get a stronger draw, and it'll come at the cost of sending more heat out the roof. Now, so we've got the cob hat put in up at the Love Shack. It's working great, and we've already come up with a bunch of thoughts on if we could, optimize that. And so if we're going to build a cob hat in the red cabin, which I can't help but think that at the PTJ this year, that'll probably be a project. I can't help but think that there'll be 8 people here at the PTJ that want to build that, want to move these experiments forward. So on the image that Andreas is showing us right now, we originally said we better make this first cob hat have kind of a pointed head. Otherwise people will set shit on it. and then, it could get too hot. So, and it goes like this. The hottest point of a rocket mass heater is the top of that barrel, the cherry on top. And people have recorded temperatures of like 1100 degrees at the cherry on different systems. And it's like, okay, that's a lot of radiant and convective heat. And it's all, the radiant heat is hitting the ceiling, and the ceiling does get extremely warm because it's a flat surface. And so it just does this radiation beam straight to the ceiling. Then your ceiling gets too hot. And then on top of that, a lot of the heat just manages to go out the roof at that point. So you're losing too much heat because the heat differential at that point is too extreme. So a lot of that heat is going outside. And it's like, that's not good. Plus, it adds to the stratification of the temperatures inside the building. So you get a lot of heat up close to the ceiling where it isn't doing anybody any good, except it's leaking out more there, because now the temperature up next to the ceiling in general might be something like 110 degrees. Whereas, we haven't even hit 70 down at our feet yet. And so it's kind of like, okay, the hat, the cob hat, it doesn't touch the top of the barrel. There's a gap. And we've kind of said, like, the gap needs to be big enough so you can cook a lasagna in there if you wanted to. But there's a gap between the cob and the top of the barrel. So now the radiant heat hits the cob, and the cob absorbs that heat. And this originally came from you. You said in your designs of the cottage rocket, and I'm going to say 7 years ago, you were telling me about the cottage rocket. And you were saying, like, rather than having a mass bench, you could put this cob blob on top of the barrel. Of course, don't have it touch the barrel. That would be bad. But you could put it above the barrel, and then rather than heating your bench up to like 120 degrees, you could heat this thing up to 400 degrees. And then there's less of it, so it works better in tiny houses or in places where weight can be an issue. And but it heats up to a much higher temperature and then carries that through the next day. And it works.
And there's a number of aspects that we can look at and point at it working and say entirely different things about why we think it's working. And when we initially started sticking stuff on top to try to capture some of that heat before it hit the ceiling, we put some big chunks of your local rock on there, and said, okay, we're going to warm those up. We're going to cook those on top of the heat of this, the barrel, and see if those will help us, stay warm overnight. And what we found pretty quickly was that the smaller chunks of rock, even a big pile of small chunks of rock, would absorb the heat and then radiate it out again pretty fast. And then we would get the biggest chunks up there that anybody could lift up there and try to stick them close together. And then the top chunks wouldn't be nearly as warm as the bottom chunks because thermally they weren't really connected. And the heat was all being absorbed by the bottom chunks. And the bigger chunks on the bottom were helping us stay a little warmer. That was promising. And we said, well, why don't we sculpt something with cob up there? And the concern that you have for the metal of the top of the barrel led to conversations about how to have that hat absorb the heat but not trap heat there and make that the top of the barrel too hot for the metal in there because the metal will fall as it gets hotter. And personally, I they call me Uncle Mud because I do everything I can with cob and I would just use the top of the barrel as to cast a piece of cob and stick it up there, and then chuck the barrel lid someplace else, because the cob can withstand that direct force, and we can absorb 600 and 700 degrees temperatures rather than the radiant heat from the outside of the barrel. That can make that hat work better. I think. Have you done that? Yeah, I love it. I love it. In fact, the cottage rocket initial design was also to wrap some cob around the riser inside, and we didn't have insulation inside the riser like we should have, so it wasn't as optimal of a burn as it could be. We've improved that since then, but having the barrel full of cob as possible I heated my Fisher Price house for 3 years with just a cottage rocket, a barrel full of cob rocket heater. No other insulation around the riser, nothing else. It's just cob with hollow spaces for the riser and the tubes going down. So we could, and then cob on top of that hollow space where the exhaust comes out of the riser, and on top of that manifold where it goes back down. The more, especially in a tiny house situation, the more of the heat we can keep in the system past we want a little bit of instant gratification heat so that whoever's feeding it will continue to feed it. It'll get a little warmer and warm up the space so they're not frustrated. But the more of that heat that's stored in mass rather than just let off into the ceiling and into the air up high in the room. One of our cottage rocket designs actually has a hollow metal manifold underneath the burn chamber. So the exhaust has to go down through there and radiate heat down at foot level before it goes off into the thermal mass bench or whatever. But having a mass around our barrel, having that hat if we design an airflow up and around to protect the metal, we can actually. I like the idea of a mullet, a cob mullet on here, where we got airflow coming up underneath this mullet toupee, kind of protecting the back of the barrel, so that heat that's been radiating into the wall is all just kind of being trapped in the air that gets sucked up and under the hat and comes out the front through that nice little slit that you guys have built in there, and just get pushed into the room where you're gonna where it's gonna be more available to you. And maybe we even go as far as having the intake for the air that comes up and cools the top of the barrel at the bottom of the far corner of the room. So the coldest air in the room gets sucked up over that, over the top of the barrel and out into the room. We keep more heat in the system further, even being willing to send some up the chimney, but trap more in the mass, and give us a good draft, without warming the space up too fast so that people stop feeding the fire.
So you said something about making a cob blob and then replacing the barrel top with the cob blob.
Yeah.
And I've got two big objections to that. Having never tried it before, this is just me being a whiner. Okay. Objection number one. In order for that cob blob to hold heat long enough, we're talking about something in the realm of 160 pounds to 300 pounds. That's a big ass blob to move. My second objection is that, for most of the system, once it's running, the whole thing goes pressure negative, except right at that point, except for in the riser and just above the riser. That's a fairly high pressure system because it's going to push up the riser, then push down the barrel. And so that's a spot where if you don't get a really great seal, things could be yucky. And, that makes me nervous as hell, especially when you start talking about, well, once we heat this up, which we're going to heat it up a lot, these different materials are going to, expand and contract at different rates. And it's like, so the opportunity for leaky bits, including leaky bits months down the road forming, makes me nervous. And so I have a third bit to add to all this. We've done the cob hat where we keep the metal, and then we've got that gap in there, and we've got 2 pieces of angle iron in there so you can put the lasagna on the angle iron so it's not sitting right on the barrel, thus causing it to potentially spall. But you could put a lasagna in there, or cookies, or pie, or all kinds
of which are very compelling arguments. Lasagna and cookies and pie. Absolutely.
There you go. The list goes on, and and I kind of feel like, while we haven't tested that function yet, it's ready to be tested. And I'm very excited about it. I think it's going to be a big win. And so, I kind of feel like, this way you maintain the seal, and at the same time you can bake things in there if you want. And if you don't want, that's fine too. Everything is, clearly the results right now are spectacular.
Absolutely.
So,
absolutely.
For the one in the red cabin, I'm kind of thinking like, okay, I've got my vague wants, and I want to be able to get the cabin up to temperature faster. So basically my general theory is I want to burn the same amount of wood, maybe even more wood, in about half the time in order to get the cabin to heat up faster. And this will also mitigate the cold plug issue. There's not really an issue right now, but I'd like to make it so that it's easier. It's more delightful. I want to improve the probability that somebody can stay in there and the experience is 5 times better. Just vague betteritude. If they go and they try and start the fire, but they didn't read the directions, chances are it'll be a little wonky, but it won't be as wonky. When they try to warm it up the first time, if they happen to do that, they have a greater success. It warms up much faster. If they want to maintain heat, so they want to get up in the morning and it's still quite warm, and when they come back the following evening, it's still rather warm, and then they can start a new fire. I want all of these things to be even more delightful than what's in there right now. And I've got all this stuff in my head about how we can make that happen now that we've got a baseline. And so, which is what this whole conversation's about. All right.
Yeah.
And that leads to cob hat. I think a big part of my recipe is that, okay, if I can get the heat over to the vertical exhaust faster, it'll have a stronger draw. And with a stronger draw, it'll burn that wood faster. It'll move heat into the system faster. It'll put more heat to the existing mass faster. And then the mass will absorb more heat because it's so efficient right now. And so it's like, okay. And I'll end up with more heat getting to the vertical exhaust. So it's kind of like, all right. By doing that, by getting the whole system to go faster and putting more heat outside, then, and at the same time wanting there, because you're talking about how you want the mass to be as efficient as it is. You're very happy with how efficient the mass is at harvesting the heat. And I'm kind of thinking like, okay, I want to do even better. And we can with the cob hat. Let's build a better cob hat than what's inside the Love Shack. And by better, I mean, let's make it thicker on the top, more mass, and let's make the top flat. And now I've been saying, let's make the sides of the cob hat vertical. And you have a different philosophy, which is?
So whatever direction the surface of our radiant warm thing is facing is what's going to get warm. So if I have a triangular warm thing, then the warmth is generally going to be focused in those three areas. Square thing, 4 areas, and there's going to be these points where there's not so much radiant heat going out. A circular round thing is going to radiate fairly evenly. A dome-shaped round thing is actually going to radiate up as well as it radiates to the sides. I'm saying if we had a radiant surface that even was a little bit sloping out, a little bit conical out, so that it's radiating at the floor at the other end of the room, that's going to be where, you're sitting at your desk at the other end of the room and you're getting some radiant heat down around your legs. It's not just the bench that is the thermal mass in a building. The whole Fisher Price house is the thermal mass that keeps the building warm through the night between firings. Not just the mass bench. And in a little room, in a little tiny house, every bit of mass that absorbs heat, slowly releasing it, contributes to how long you're comfortable. And if we can radiate heat at low masses where it's going to keep our feet warm and it's going to have a farther path, more difficulty leaving the building, that heat will have more difficult path leaving the building, we're going to be happier. I would even consider building a cob hat that had slanty sides and some insulation on top of it, so that it was really not very warm up there, but this mass is radiating into the room longer because it has a less radiant surface, but it's radiating down and out into the room. And even if you've got that nice air circulation coming up under the cob hat, and out the front, maybe it gathers more heat from a cape or the mullet, as I'm saying, in the back, where we don't want heat radiated. We don't want heat radiated at the wall. We want heat radiated out at us.
Oh no, looks like your internet may have died again. So I'm gonna try to
let's gather as much of and as.
Okay.
Can you hear me now?
I can hear you now. You kind of went offline there for a sec, but all right. I do think that everything you're saying is true. I also think that the temperatures we're talking about here are something in the range of like 150. And so this 150 degree thing putting out radiant heat, it is putting out radiant heat. It's just not an enormous amount, but basically it's like, having this 12 hours of this small amount, it does make a difference. And it's amazing how it accumulates in certain places. And so then you get up in the morning, you put your feet on the floor, and you're like, the floor is warm, and this is what would cause it. So, all right, that is a worthy experiment. I'm not sure about putting something insulated on the top, but maybe. And so, but the thing is that I think other than that, we're agreeing that this
absolutely
shape, go with this design of Cobb hat that's up there in the Love Shack, only bigger, so thicker mass, either vertical sides or a little bit, like really wide at the top, coming down to a narrower at the barrel. And it's like, I could see that. I mean, we might need to round that edge a little bit so it doesn't just chip off, but,
and we can talk later about the barrel, Cobb and the barrel, but most of the oldest rocket heaters were built with barrels that were old with big rust holes in them, and that rust was patched with Cobb. I seal a lot of the places where there are cracks between the joints of the barrel and the lid with a little bit of, so we definitely have, to seal, those surfaces. But, there's a lot that we can do with with this design, that we're agreeing on for a Cobb hat, to make this work better in a tiny house. The one thing I'll be curious to see whether it diminishes our returns is, the stainless barrel has about 1/5 of the radiance of the energy transmission of a mild steel barrel. So already our stainless steel barrel is radiating very slowly into the room compared to what a mild steel barrel would be doing. So I will be very curious to see if our results from our hat do everything we were hoping, or if they're milder results because we're not getting as much radiation off the barrel already on purpose.
I think that there's a lot to contemplate there. I do think that when we're talking about a temperature, like when we're recording a temperature off of the top of a steel barrel at 1100, and then when I go to a stainless steel barrel and I'm getting temperatures of 1000, then I'm kind of thinking that it's like conductivity probably changes when it gets much hotter.
Right.
And because if nothing else, if the temperature is, if the temperature gets to 1600, the mild steel will start to spall and the stainless steel will not. So It's like clearly these temperatures are, these tests about conducting heat are probably done at lower temperatures. But I wonder if
the heat will eventually get out. So if it's if we're cooking with if we're cooking along with a good hot rocket fire, and it's 1500 degrees on the inside, it's eventually going to approach that on the outside, even if there's a lot less conductivity, because the heat will be transferred through eventually. But if the heat is transferred through slower, we'll have a lower temperature on the outside compared to what's on the inside. We're already getting a bit of that thing that we like of having more heat left over to go through the rest of the system into our mass and then up our chimney to make things work better for the tiny house. We're already getting more of that with the stainless than we are with the mild. I'll be very curious to see how much we're getting of that, and how much the improvement is, how much improvement is made by putting the cob hat on. Will it be like putting another hat on top of a hat, or will it be putting another hat on top of a very poor hat, so we're able to see how much happier we are?
Hi, this is Mark. There are a lot of reasons to get angry these days, but I prefer to focus on the positive things that we each can do to make this world a better place. The book Building a Better World in Your Backyard, Instead of Being Angry at Bad Guys, is a great resource for just that. Instead of throwing my arms up in frustration at governments or big corporations, there's a list of ideas that we each can tackle to affect change. Information about this book and other resources can be found at permies.com.
That's a very good point. At the same time, as I'm going through my wish list, I've got the thing where it's like, okay, I want to have a stronger draw, which means I have to give up some efficiency. And, but I think I can get that efficiency back and then some by adding a cob hat. It might not perform as well as in the Love Shack, but then again, we're going to make a better cob hat. And so I'm kind of hopeful that it'll perform better, but it's also, I think that the red cabin is about 40%, it has 40% more cubic feet than the Love Shack, but the Love Shack's also a 4-inch rocket mass heater, whereas this is a 6-inch. So,
right.
And also this has already it has a big mass. And so we're going to lean on that mass and add in the cob hat as a mass. So I'm kind of thinking this overall recipe that I'm working towards here, is going to give me all the things that I want. It'll heat the cabin in less time. So you'll get up to your initial temperature faster. It'll have an overall stronger draw. The cold start stuff will be mitigated. Cold plug stuff will be mitigated. And will carry more heat through till morning, all of them. And it's and I think a big part of that recipe is going to be to put in a cob hat.
Yep.
I think that, as long as we're on the topic of how do we make this system less efficient? Well, one way would be to make the mass 30% smaller, but that's a lot of work and I don't want to do that. Another would be to take out maybe 60% of the cob that's inside of the mass, but that also sounds like a lot of work. And so I'm gonna let it go. I think that a good way is going to be right now the stratification, the juice box straw going down into the stratification chamber. I think it's got a good 8 inches. It's going down 8 inches right now, is a guess. And you're nodding, so my guess is confirmed. I'm going to say let's take it to 4. And now the whole system will be less efficient. And that's a little bit sad, but it'll make it so that we get a much stronger draw. And so we'll be able to heat that space faster, but with the same amount of wood. So, that's my current plan to make the system less efficient for the sake of being able to mitigate cold plug stuff, as well as being able to have a stronger draw so that way we can heat the space faster. So it'll use the same amount of wood, but because there's so much more air blowing on that wood, it'll burn faster. All right. Next up, in order to help mitigate cold plugs, there is a critically important ingredient missing from this build. And it's one of those things where everybody says, oh yeah, that person will take care of it. And then they're pointing back at the first person saying that person will take care of it. And then, together, if they ever got together and shared notes and realized that, nobody was going to do it, they would point to future people. Oh, the future people will do it. Let's not worry about it. Let's focus on, because it's the most boring part. And that is that there's not currently a sign there that gives people instructions on a cold start. And so we got to have that. That is, I think, so important. That makes all the difference. Having that sign, it just transforms the whole thing by having a proper sign describing how to do a cold start.
So if we had a sign that said how to do a cold start and it included how to use the priming port that we haven't talked about installing yet, that's where I would start.
Well, and I think cold start instructions have to mention that.
Mm-hmm.
That's part of it. And there has to be a port to be able to prime the vertical exhaust, which the current one has a port to prime the vertical exhaust. It's just not great.
It's weak. We moved it so that we could to put it, and we put our we put our juice box there instead. And you and I did some design charrette around that as to a couple weeks ago as to how can we put a really good a priming port in there that would also act as a clean out, and that right there might mean that we don't have to make the mass any less efficient. We just get the exhaust good and hot before firing. We put good instructions up for that, and then when we fire it, it's rocketing very nicely and absorbing and slowly releasing more heat in the cob hat and more heat in the mass bench. And if it's absorbing and releasing more heat from both of those places well enough, then we don't have to fire the heater as long, which would be also delightful.
So I think that the clean out port needs to be removed and then replaced with another clean out port that is about 11 inches closer to the vertical exhaust. And it makes it easier to prime the vertical exhaust. That's my thinking at the moment. So that's one component to help make it. It's like it won't change much other than just making the priming of the vertical exhaust easier. There, you can kind of see it in this picture that Andreas has put up. There's that priming port, which is also a clean out, that is on the far end of this picture. And it's like, let's just come up with a way to get it to be much, much closer to that vertical exhaust. And then that'll.
Now, one of the retrofits that we talked about is putting in a T in there. In this case, we might have trouble finding a spot that's easily accessible at the base of the vertical exhaust, which is the best place to put a priming port. But we talked about a T with a cap, and that cap has a little support on it for your Bernie bits you can pop the cap off and stuff some flammable stuff into this little holder that's part of the cap, and you light that and shove it back in there, and it's just sitting there inside of there, giving us our prime if we can't get to the bottom of the exhaust. So we'll have to see which one works better for us.
I'm now on to my last note for improving this rocket mass heater, and this is about making this rocket mass heater more handsome, in my opinion, and more handsome. I think that the heat shield is not particularly handsome, and we use the heat shields a lot to be safe, and they are wise and they're good engineering, but it's at the same time, it's like, and you know, this is what conventional wood stove should be doing too, but they do other things, and or they don't do anything at all, which is kind of like, that's dangerous.
Mm-hmm.
But yeah, there we go. Here's a picture. It's even got a finger pointing at the heat shield. That's handy. So I think that heat shield is ugly, and so at the same time, I'd like to be able to make it so that when the fire is burning, I'd like to have a stronger draw, especially in the first 2 minutes, to help mitigate cold plugs. And so I've kind of got this idea of, what if we kind of made a bit of cob that kind of would touch the vertical exhaust and touch the barrel in such a way that there was an air gap that went between the vertical exhaust and the barrel, but was surrounded by cob and capped at the top. And part of what I'm thinking is that as the barrel starts to heat up and it puts out 200 degrees at the beginning, then that 200 degrees gets kind of held in this capped air pocket, which in turn heats the vertical exhaust. And then as the temperature goes up and up and up and up and up, then the vertical exhaust temperature goes up and up and up and up and up. And it creates a stronger draw. And then beyond that, the cob can be expanded in such a way to be a bit of what we've been calling a cape, which is just cob touching the barrel. And so the idea is that it'll heat the cob. So if we put something on that's 3 inches thick, that's touching the barrel. And by touching the barrel, I mean within 2 weeks, there will be a 1/3 of an inch gap between the cob and the barrel, because the cob will have dried and shrunk and other things will have happened. And so there's going to be this gap between the cob and the barrel. And so, but it'll still be 3 inches thick, and it'll probably be about 4 inches away from the wooden wall. And I think that the hottest point on the outside of that cob, so like the outside of the barrel, is going to have spots that are probably going to be something on the order of 400 degrees at the top of the barrel. I'm just guessing. 400, 440, somewhere around there. That'll be the hottest we will ever see on the top part of a barrel on a 6-inch system that is stainless steel. That's a guess. And then the cob is going to absorb a lot of that and spread that out. And so I think that the hottest point on the outside of the cob is going to be something on the order of 130 degrees. And then as it radiates that 130 degrees out towards the wood will be heated to something on the order of 95 degrees, which 95 degrees is less than a 105 degree day. Therefore, I think that wood will now be so safe that we will no longer need the heat shield. Now, of course, the thing to do is we build it and then we test it and we kind of get an idea of, like, is it safe? Did it fall within what we thought? Is it off by a little bit? Is it off by a lot? Things like that.
Absolutely needs testing. Absolutely.
Yeah.
I will. Most of the actual rocket heaters that I have seen cause building fires have been because wood was too close to a mass bit, not even the barrel bit, but a mass bit that built up heat over time. So it's, it's negative 20 out. So people are firing the thing 24 hours a day, sleeping on the mass, things like, sleeping on the mass bench and firing it, things like that. So I tend to be, and also it was places where that mass, made it hard to check for heat buildup, between the wood and the mass. And also over time, the continued, exposure to heat made the wood more flammable at a lower temperature until one day, 10 years later, boom. This is a very small set of actual happenings because there are so few, building fires that have happened because of rocket heaters. But it has me concerned, and I will be very happy, to be testing this to see, if we can use less shiny metal and use more cob, for, functional heat shields. I've used pea gravel as a functional heat shield. And so I know that there are, other ways to get, to slow down the heat other than reflecting that radiation. But those sheet metal, heat shields are extremely effective. And so we're going to have our work cut out for us to see if we can do something different.
So I'm trying to imagine a mass being heated to a temperature high enough, because my understanding is that if you expose wood to a temperature of, like, it's 140 degrees on the wood, and you can do that for years, eventually the wood will ignite. But it's got to be 140 or better, spread out over years and years and years and years.
Yep.
And so in order for a mass to be able to be hot enough that it will radiate out a temperature that would hit that wood at 140 degrees, that mass has got to be at a temperature of something like 220 is a guess.
Yep.
And that would have to mean that, there's an exhaust manifold right there.
Nope.
And the amount of No.
What if the mistake was that generates this type of stuff is thinking, is that if you're building your heater and installing the J-tube in a mass of cob, and you've got 6-8 inches of cob below your manifold, below anything with flowing exhaust, you're thinking, well, that's far enough away. But what will happen is that J-tube gets mighty hot, and eventually it gets, I mean, because that J-tube is over 1,000 degrees, hopefully, and the bottom of that firebox, which is 6, 8, 12 inches away from the wooden floor, is slowly and surely building up that heat to the in all directions, including straight down. And what happens is that the bottom side of the wooden floor catches on fire.
Okay, but you just said it was the mass. It was the mass. So it was not the mass.
Our cob, our cob hat, and any mass that touches our radiant barrel is subject to that kind of temperatures. And will not cool down quickly like a piece of sheet metal will. So the heat will concentrate and cause fires using, and this is true of brick or stone or anything massive. I'm not talking about the mass bench. I'm talking about anything massive being in close proximity to the high temperatures that we're talking about.
So the problem where you saw flammage or something went bad with a rocket massacre, it was wood that wasn't protected from the burn tunnel. It was not, because I thought I heard you say the mass, and I was thinking like that's something beyond the manifold.
No, there's multiple places.
Beyond the manifold, you've never seen a problem.
So beyond, when you get to the mass bench, it can still be 300 degrees within that mass and under that mass, and that can lead to a problem. But any place within that's any mass that is within a foot of the burn chamber, and any mass that is touching any mass touching our radiant barrel has the capability of getting to fairly high temperatures. And if we're going to use mass as a thermal break, so that we're not radiating directly at wood, we need to be very careful that mass doesn't allow heat to build up and cause us the problem. Now, if there's an air chamber, there's an air passage between the radiant barrel and also air passage where the air gets warmed up and gets moved out, and cool air has to come up and replace it on the outside of our cob radiant barrier. We're probably going to be just fine, but we need to have data from firing for a long time before we and not building up heat from being in close proximity before we go and put that in a tiny house.
So I think that the amount of heat that comes off the barrel is enough to heat the wood above 140 degrees.
Yes.
And then if we slap 3 inches of cob on the side of the barrel, then I kind of feel like what's going to be on the outside of that cob if you ran that thing 20 hours straight, what's going to be on the outside of that cob is going to be something on the order of 250 tops. probably, I mean, if you do a 1 hour burn, I'm kind of thinking like maybe it'll get up to 180, and then if it's 180 and it's radiating out that 180, the wood, which is going to be about 4 inches away, is probably going to be hovering around 95 or so. And so I'm kind of thinking like it's not going to be an enormous amount of heat, and it's something where it's like this barrier will mitigate it. Now, of course, if you do only an inch thick of cob, it's going to be much hotter. And but I'm kind of thinking about like, okay, much hotter. What if we do an hour burn or a 2 hour burn and measure the temperature of the wood and see how we did?
Right.
But with 3 inches of cob, I'm thinking like, if we forget to measure it, I think I'm going to be okay. I think we've got so much buffer. I think we're going to be all right. But I could be wrong too.
Well, and that's where we want to find out, because if the 3 inches of cob is close enough to our very hot radiant surfaces that it concentrates heat, that outside of that cob can be 300 or 400 degrees eventually. And we're not talking a 1 or 2 hour burn. That's not really a concern. The places where I've seen things that worry me is when people are just running the thing straight out for just because it's negative 20 outside and their house was poorly insulated, because that happens a lot. And
right.
So that's kind of where we have to design for, is where the Gilligan factor is going to show up catastrophically, not where it's probably going to be okay. So I'll be. This is a test that I will be excited to see the results of, to see what can we do with these materials, to not have sheet metal hanging on the wall, and where's the limit of what will work.
Well, the other thing is that if you take out that sheet metal heat shield,
yep,
and then you put in this cob cape. We've been calling it a cape. So it's just on that, it's just between the barrel and the wall. So the barrel is currently heating that heat shield, which then, the heat goes up, straight up from the heat shield. And so instead it would heat this cob cape. And then, the cob cape will help in carrying heat through the night. And so,
yeah, and if the cob cape is brought up as an air conduit at the top and at the bottom to draw air across our radiant barrel and out into the front of the room, out in front of the heater into the room underneath our cob hat, that's gonna be putting heat where we want it.
So my bladder says our recording today is done. It's sending strong messages right now.
Tell me how you really feel.
If you like this sort of thing, come on out to the forums at Permies.com, where we talk about rocket mass heaters, homesteading, and permaculture all the time.
In a world on the brink of social collapse, one website stands above the rest to fight back the zombie horde of corporate trolls. Permies.com. Take back control of your destiny and protect your loved ones from the toxic gick coming at you from all directions. Strap on your overalls and start building that bunker of abundance with the good vibes and friendly, helpful insight found at Permies.com.